So guys, we are starting off with the concepts of fundamental particles. And for that, what you need to understand is that it has a long history, and this theory of about the smallest matter particle has evolved and come a long way. So it was basically early 19th century when Dalton gave his theory about the atom, and he suggested that the smallest particle of any particular matter, if you keep on cutting it into smaller sizes and you'll come to the smallest ever particle, he called it atom. So that was a point where scientists used to believe that the smallest particle is an atom. And then almost like it took a century for J.J. Thomson to perform an experiment where it was, he observed cathode rays and he identified that the particles involved in cathode rays were very small. They were almost 1 upon 1800 times the size of a hydrogen atom. So that led to the fact that there's something smaller than that, and then Bohr suggested an atomic model, and that was early 20th century, where he said that there are protons and neutrons inside the nucleus, and electrons are orbiting around the nucleus. And but I mean, that moment where J.J. Thomson discovered electron as 1 upon 1800 times the size of hydrogen atom was the point where the concept of the fundamental particle started. And then since then, it has come a long way. A lot of different small particles have been discovered. And so just like, I mean, when you do chemistry and you have to deal with a lot of elements, and obviously to cater with that and to classify them, you make a periodic table. So just like this is a table that you don't need to learn, but you need to be aware of the fact that there's a table that contains the list of all of the fundamental particles with their basic classifications. So, so as I said, I mean, theory has evolved, and up till now, scientists believe that the smallest particles are the fundamental particles. So, and this particular table gives you the list of all the fundamental particles. So this like 4 times 4, 16. Every particle is going to have an antiparticle. So it's like if you have this particle over here, this is called up quark. So there would be an anti-up quark as well. There's a down quark, so there's going to be an anti-down quark as well. There's a charm quark, and there's an anti-charm quark as well, and so on and so forth. So it's like, and scientists are still working on this particular idea to sort of identify all of the fundamental particles. And working on that, of course, it's like, if I'd say, well, how are these fundamental particles are being discovered? So it could be more like if you were a very curious child and you used to play with your toys, and then after some time playing with that toy, if you used to get bored, which I did used to, and if the next moment was where my level of curiosity arose, and I wanted to figure out what was inside that particular toy. What is it made up of? And even a child's brain can work on that if I need to find out the composite components of that particular toy, what I used to do was to smash the toy and see what's inside. And that is what scientists are doing. They want to see the smallest particles, so they smash particles in particle colliders. And as these particles collide at high energy, they break up and hence you are able to identify the smallest fundamental particles which any matter is made up of. So the thing is that, I mean, this is a long list. You need to be aware of the fact that there's a long list, but you don't need to be knowing all of these as far as your AS physics course is concerned. You need to be not to be knowing all of them. But yeah, I mean, just a bit of an idea that if you could see a bit of a color coding over here. So there's a classification. This is over here. These are not matter particles. These are called energy particles or exchange particles. So whenever one matter exerts a force onto the other matter, what they do is that they exchange these energy particles. And these are the examples of the energy particle. And then this side of the table is basically the matter particles. And these matter particles are called fermions. That's the name given to them. So, of course, there's a learning involved here. You have to learn the names. But there are matter particles which are called fermions. And then these fermions are further classified into quarks and leptons based on their sizes. So these are comparatively bigger particles, quarks, and leptons are comparatively smaller particles. So they interact with the strong nuclear force, and they are not affected by the strong nuclear force because their masses are really, really small. That's the reason for this particular classification. So energy particles, matter particles, and matter particles into small and big matter particles. So these are big matter particles which are affected by strong nuclear force, and these are small matter particles which are not affected by strong nuclear force. So let's come to what's really relevant to our syllabus. So I told you that the main classification in the beginning of fundamental particles is bosons, which are exchange particles, and fermions, which are matter particles. And bosons there are different types of bosons, and this is an increasing order of force. So we recognize that there are 4 forces in the universe, and the weakest force of the universe is something that you experience the most as a gravitational force. And this is a hypothetical particle. It has not yet been discovered, but hypothetically, we believe that one of the particles would be a graviton, which is involved in gravitational force. But these are the discovered ones. So there's a gamma photon for electromagnetic force. There are W plus minus and Z bosons, which are for weak nuclear interactions. And then we have gluons. Gluons are for strong nuclear interactions. This is basically that particular force which holds the nucleons together. So if you know that there are very, very strongly repelling protons inside the nucleus, inside a very, very dense small nucleus, then how come so many positively charged, strongly repelling protons are confined in such a small, dense nucleus? So that means as they are being repelled, that repulsion is being countered by another force which is even stronger than that and must be an attractive force. And that force is called strong nuclear force, which holds the nucleons together. The force that keeps protons and neutrons inside the nucleus attracting each other is called a strong nuclear force. And the exchange particle for those strong nuclear force are called gluons. So we have like these, to be very exact, we have 3 major classifications of bosons and 1 hypothetical particle, which is graviton. So as I was trying to tell you that, I mean, and I showed that to you in the table as well, that fundamental particle has classifications, bosons and fermions. And bosons are the exchange particles for forces. So one classification is exchange energy particles, and the other classification is the matter particles, which are fermions. So they're called fermions, the name of them. You have to remember name. So fundamental particles are bosons and fermions. Fermions are the matter particles. And then these matter particles also have another classifications as leptons and quarks. I tried showing that on the table as well. Leptons are not affected by strong interactions, and quarks are affected by strong interactions. So there are, I mean, you would have seen there are many leptons and many quarks, but most important for us are up and down. And so if you have up, and there's also one more important for us, that's a strange quark. So you can also mark another quark that's a strange quark to remember. So not that these are the only quarks, but these are the quarks that we need to be aware of for our AS physics syllabus. So quarks are affected by strong interactions, and the quarks that are important for us are up quark, down quark, and strange quark. And since we have to understand up, down, strange, I told you every particle is an antiparticle. So an up would have an anti-up quark, and down would have an anti-down quark, and strange would also have an anti-strange quark. So the reason of this classification is because of their types of interactions. So strong interactions and not affected by strong interactions, quarks and leptons. And despite there are more quarks over there, we need to sort of remember 3 quarks and their anti-quarks, up, down, and strange. Up and down are most important for us. And then leptons, so there are again long list of leptons if you go back to that table. But the ones which are really, really important for us are something we've already talked about while we were doing beta emissions. So when there was a beta minus emission, alongside that, with the beta minus emission, you had an anti-neutrino emitted. And with the beta plus emission, you had a neutrino being emitted. So these are the leptons. These are not affected by these strong interactions. So you'll see that these are being affected by the weak interactions.